Hello. Hey guys, I'm going to start with my presentation. It's about design choices in Eth2.0, and this is basically to inform smart contract developers on Eth1 today about what changes they can expect going forward with Eth2. My name is Aditya, and I'm a researcher at the Ethereum Foundation. So let's start with what were the design requirements of this new scalable sharded blockchain system called ETH2, and how the specific implementation achieves this, and what this means for smart contract developers. So the two basic requirements are scalability and security. And the specific requirements for scalability is superlinear sharding, which means that the total throughput of the system is superlinear with respect to the throughput of a single node. So if the capacity of a node is C, then the capacity of the entire system should be like more than O of C. There were some issues with this definition, so I kind of changed it to this, which is if the capacity of each node increases k times, then the capacity of the total system increases superlinearly with k. So, k log k or k squared, something like that. What this means is even if, what this means is basically there is no node which linearly affects the throughput of the system. So there are no supernodes, there are no sequencers, there are no linearizers. There is no one point where, most of the computation in the network is happening, which would manifest in this linear dependency. And the second requirement is, of course, security. And we want that the security of the system is uniform in all parts, meaning all shards or all partitions or whatever parts you have. And it should correspond to consensus safety across all nodes in the system. So not just that specific shard or that specific partition, but across the entire number of nodes across all parts. And to achieve this goal of sharding, what we do is take the entire state space and cut it up into partitions and call them different shards. And we also do that with the entire validator set. We form subsets of this validator set and assign them to specific shards to be responsible for those shards in some sense. And for security, we have something called the beacon chain. And the beacon chain is basically the source of consensus safety in ETH2. It's the only place where consensus happens. And since we had this requirement of the security of the system is uniform and is equivalent to consensus safety across all nodes, if this is the only place where consensus takes place, all nodes must participate in it. So all nodes form consensus on the cumulative state of all shards, which is some accumulation of states. So that accumulation, we'll see whether it is just like plain concatenation of state or some other type of accumulation which compresses it. And if you combine this fact of how the beacon chain works with the scalability requirement of superlinearity, then this immediately leads to two conclusions. The first is the data consideration. So the beacon chain can't contain the entire data of the system, because if it does, and everyone is validating the beacon chain, then each node in the system is going to contain the entire data of the system, which breaks like the superlinear data throughput that we want. And the other is similarly the execution consideration, where if everything in all shards, all transactions from all shards get executed in the beacon chain, then all nodes in the system are executing all transactions in the system. And so this breaks superlinear execution throughput, which is not what we want. So what we do have is the beacon chain where all validators participate and form consensus, but they do so on a compressed accumulation of the state, which is Merkle roots of the shard. Not entire shard blocks, not entire transactions from shards, only Merkle roots. And as far as execution goes, you don't execute anything in the beacon chain. No transactions are ever seen, observed, or executed inside the beacon chain. And within shards, you don't have any consensus because, well, you already found consensus in the beacon chain, and there's no point to like forming consensus in the shards. But since the beacon chain doesn't do any other type of validation, it doesn't check whether transactions are valid, if like users are doing something nasty, we need that shard committees validate blocks, which means they verify transactions, like propose blocks, accumulate transactions and propose blocks, stuff like that. And well, if you aren't forming consensus in shards, then how does a shard chain grow? So what we do is sample validators from the entire validator set and assign them to specific shards. And instead of forming consensus in shards, they just vote on blocks. So it's not a like consensus algorithm as such, it's just voting. And if you have some sort of a majority, then that block is considered like good and is included in the beacon chain. So roughly, it looks something like this. So you have all validators on this top left corner. You sample them, get a shard committee, which is responsible for like some shard. Then that shard committee does 2/3 voting on blocks in that shard. You get a shard block. That block is good. Then you cross-link this block in the beacon chain, which means the block is like included in the Merkle roots. The Merkle roots of the shard blocks are included in the beacon chain. And then all validators form consensus on it. So as you can see, no consensus in shard blocks, no execution in beacon chain, execution in shard chains, and consensus only in beacon chain. So that's roughly the design. The point of this is showing you, okay, how many smart contract developers in this room? And how many Eth2 researchers or like blockchain researchers in general? Okay, cool. So the point of this is showing you roughly how the system works and what this would mean for smart contract developers and why we can't provide certain things that you would expect that you see in ETH1. So there are certain changes to the developer experience. For example, static state access. This is something that the Quilt team talked about yesterday, but I'll elaborate on it later. And so these are just new changes to the developer experience. And there are some things that were possible in ETH1 that probably won't be possible in ETH2. Something like synchronous calls to any other contract in the system. So think about contracts in one shard trying to talk to contracts in some other shard in some other part of the system. Conceptually, this means like you have a big network, you have partitions in the network. The partitions are in some sense disjoint, although like they have some point of coordination, which is the beacon chain. But like intuitively, since there is no execution in the beacon chain, it's kind of hard for synchronous calls to happen through this central point of coordination. So these are hard to do, and I'll depict why. So first, actually, let's dig into static state access. Oh, it's synchronous. Okay, let's dig into synchronous cross-shard transactions. So the basic problem is if you send some like transaction from shard A into shard B, what you want is transaction is included in shard A block, then shard B validators or block proposers see that there is a transaction that's incoming, and then they apply it, and then do whatever they have to do. The basic problem is how do you make the other validators on the receiving shard aware that there is something that they should look at? Because what we said initially was in order to get scalability, we separate committees of validators, and they are responsible for entirely different shards. So validators from shard B are not supposed to look into data from shard A. So there is one like cheap hack that we can do. Just put these transactions into the beacon chain. What that achieves is since all validators are a part of the beacon chain, so everyone on shard A and everyone on shard B is always a part of the beacon chain. They can always refer to it as like the coordination point. And if you include these cross-shard transactions into the beacon chain, then, well, everyone is aware of it, and you don't have to worry about this problem of, how to make it available to the receiving shard. So it seems like it's kind of impossible without including more information than only Merkle roots, as we do right now, in the beacon chain. So you would have to include like the entire pre-image of that transaction, not just Merkle roots, because Merkle roots don't tell you what the transaction is. And basically this breaks superlinearity, right? Because now you're putting plain old data into the beacon chain, not Merkle roots, which means everyone like bears the entire burden of that data, which is not good for superlinearity. So that's like the basic problem with cross-shard transactions. Static state access. This is something that probably might not be aware of. So I'm sure you guys know what stateless execution is. So nodes in the network don't hold any state. State storage is probably the biggest pain point of Ethereum 1. So Ethereum 2 and 1.x is moving forward with stateless execution, where each transaction provides the state that it needs. So all the data that you need to execute transactions is provided in the transaction itself. Just like, think of it as like what light clients do. Whenever they see something they want to execute, they ask for the data. So nodes in the network don't need to be aware of any other data except the state root. They only need the state root to execute transactions by verifying witnesses to the data of the transaction. So the transactions must include witness data for all parts of the state that they access. So now it introduces some problems, and let me depict some situation that might occur. So this is not static state access, this is dynamic state access, and I'll show you what it means. So you have this transaction 1 here, and you have some stuff going on there. Then you have this instruction which loads a pointer from an address in memory in storage. So you do sload address and assign it to this variable called pointer, and then your actual data is at the location, at the memory location of the pointer. So first you load the pointer from storage, and then you load the data from storage from the address of the pointer. So if that's the transaction, the witness data should be the Merkle branch which links the state root to the storage location at ADDR, which is the pointer, and it must also provide the Merkle branch to the storage location at pointer, which contains the data that you want to load. So you have this one such transaction which you submit, and what happens next is you have this other transaction, transaction 2, which updates what exists at memory location ADDR. So the pointer that you were trying to load from memory load from storage has now changed, which means that the address from which you'll be loading your data is going to change, which means that, so this is all if transaction 2 is included before transaction 1. So if the storage at slot ADDR changes, it gives you a new pointer, then then the data that you're trying to access is from a different location. Basically your witness is now invalid because it doesn't have a Merkle branch to the new pointer. So transaction 2 is updating the pointer that you are accessing, and since that's your witnesses don't contain this storage location. And so now block producers have this big dilemma of how to order transactions. And it's super inefficient to go through each and every transaction and find out like what order works, what order doesn't. If something doesn't work, then fetch new witnesses from users or other parts of the network. So this is very inefficient. So what static state access does is you let transactions only touch predictable locations in the storage. This means that block producers can easily update witnesses without fetching data from the network. So ideally, what would happen is block producers infer this new witness branch from previous transactions that they have seen. So if a certain transaction touches a state that a storage slot that you were trying to access, and it's in the previous block, your transaction is included in the next block, the block producer looks at the previous block, says, oh, there's a transaction that updates whatever you were trying to access, and I know the post state for that, so I'll just use that instead. So I don't need to fetch anything from the network, I'll just use that. So this kind of gives us a lot of efficiency gains. Block producers don't have to do as much work. So these are like some of the changes that you can expect. And as the Quilt team demonstrated yesterday, there's a few things that uses dynamic state access today. So the point of this talk is that the primary objective of ETH2 is producing a scalable and secure blockchain system. And it's only a secondary objective to produce execution behavior that ETH1 devs are familiar with. That is not the main point of ETH2. Yeah, and don't freak out. This is okay. You'll be all right. It's not that bad. And the moral of the story is there is no other blockchain that provides the same strong security guarantees and super linear scalability that offers like synchronous cross-shard transactions or dynamic state access, for example. And this is actually a point of contention, so I'm going to give you a trigger warning. These are my opinions. There is no other blockchain that I know of that provides the same strong security guarantees and super linear scalability, which offers these things such as synchronous cross-shard transactions. That's the end of my talk. Thank you. Reach out to me on Twitter at @IDAsk if you have any questions, and I'm open for questions for the rest of my time. We can adjourn if you don't have any questions. That's fine. Yeah, sure. That works.